The universe seen close up is anything but smooth. Zoom out beyond the scale of single galaxies, past the clusters where hundreds of them swarm together, and a breathtaking architecture emerges. Galaxies strung along luminous filaments tens of millions of light-years long, filaments meeting at dense knots, broad sheets or walls of galaxies stretched between them, and filling most of the volume, vast, nearly empty voids. This is the cosmic web, the largest pattern in nature, and its existence poses one of cosmology's deepest questions. How did a universe that began so nearly uniform come to be so intricately structured? The answer is a story of gravity and time. The web grew, over billions of years, from almost imperceptible ripples in the density of the infant cosmos, fluctuations of perhaps 1 part in 100,000, imprinted in the first fraction of a second, which gravity slowly amplified into the clusters, filaments and voids we map today. This chapter traces that growth, from the faintest primordial seed to the fully formed web. To speak precisely about lumpiness, cosmologists need a language, and it begins with the density contrast, the fractional amount by which the density at a point exceeds, or falls short of, the average density of the universe. Where the contrast is positive, there is an overdensity that gravity will grow, where negative, an emptying void. But no theory can predict the density at a particular point. It can predict only the statistics of the fluctuating field. So cosmology decomposes the density contrast into waves of every wavelength and asks how much fluctuation there is on each scale. The answer is the power spectrum, the variance of the density field as a function of scale, the single most important statistic in the subject. A large power on large scales means abundant structure spread across great distances. The shape of the power spectrum, rising to a peak and falling away, encodes the entire history of how structure grew. Nearly everything cosmologists measure about the cosmic web is, in the end, a measurement of this spectrum. The same information, expressed in real space rather than in waves, is carried by the correlation function, the excess probability, over a purely random scatter, of finding one galaxy at a given distance from another. A convenient single number distills the whole spectrum, the amplitude of density fluctuations smoothed over spheres about 8 units of scale across, written sigma rate, whose measured value is close to 0.8, but a subtlety shadows every such measurement. Galaxies are not faithful tracers of the underlying mass. They form preferentially in the densest peaks of the invisible dark matter field, and so they cluster more strongly than the matter itself, an effect called galaxy bias. Luminous red galaxies, favored beacons of the great surveys, are roughly twice as clustered as the mass, fainter galaxies less so. Disentangling this bias from the true clustering of matter is one of the central labors of survey cosmology, and much of the art of the field lies in choosing statistics, like the acoustic scale, that survive it unscathed. Gravity only amplifies the fluctuations the universe was born with, so the theory needs a set of initial conditions, and the leading account of their origin is cosmic inflation. In this picture, a fleeting burst of accelerated expansion in the first instant stretched the quantum jitter of a primordial field up to cosmic scales, seeding fluctuations on every wavelength. The simplest inflationary models predict a spectrum that is very nearly the same on all scales, the scale-invariant form first guessed by Harrison, Zeldovich and Peebles, but not exactly so. Because the field driving inflation rolled slowly but not infinitely slowly, the theory predicts a slight tilt, a touch more power on large scales than on small. The measured value of that tilt from the Planck satellite is about 0.965, decisively less than the scale-invariant value of 1, by more than 8 standard deviations. That small red tilt is one of inflation's signature predictions, and its confirmation is among the strongest empirical footings the whole framework possesses. 2 further properties of these primordial seeds shaped everything that followed. First, they were adiabatic. Every component of the cosmos, the photons, the ordinary matter, the dark matter, shared one common fractional ripple, rather than being disturbed independently, and observations of the microwave background confirm it. Second, they were very nearly Gaussian, drawn from the bell-shaped statistics of a random field, which means the power spectrum alone captures essentially all their information. There is no hidden structure in higher correlations. Searches for departures from this Gaussian simplicity, in the microwave sky and in galaxy maps alike, have so far turned up nothing, consistent with the plainest single-field models of inflation. So the starting point is beautifully simple, a nearly scale-invariant, adiabatic Gaussian spectrum of tiny fluctuations, the same faint whisper of structure on every scale. The task of all that follows is to watch gravity take this featureless seed field and sculpt it into the cosmic web. The engine of that sculpting is gravitational instability, and its logic is simple. A region slightly denser than its surroundings pulls a little harder, draws in nearby matter, grows denser still, and so runs away toward collapse. Opposing this runaway is pressure, which tries to smooth fluctuations out, and the balance between them was captured long ago in the Jeans criterion, named for James Jeans. There is a critical length. Fluctuations larger than it are unstable and grow, while smaller ones merely oscillate as sound waves, pressure restoring them before gravity can win. The critical length depends on the sound speed of the medium, and here lies one of the great virtues of cold dark matter. Being effectively pressureless, dark matter has a critical length, near zero, so its fluctuations grow on all scales, unopposed. This is why cold dark matter is so efficient a builder of structure, and why it, rather than the pressure-supported ordinary gas, forms the scaffolding on which the visible universe was raised. Set this competition in an expanding universe and a crucial new feature appears. The equation governing each fluctuation contains three forces: self-gravity driving collapse, pressure resisting it on small scales, and a third term born of the cosmic expansion that acts as a kind of friction, a drag that slows the growth of structure. This Hubble friction is why, in an expanding universe, an overdensity does not collapse explosively, as it would in a static medium, but grows only gradually as a slow power of time. When the working out is done for the matter-dominated era, a result of beautiful simplicity emerges. The density contrast grows in direct proportion to the scale factor of the universe. As space doubles in size, the fluctuations double in strength. And this growth is the same on every scale, so a single growth factor describes the amplitude of all linear structure at once. That clean proportionality, structure growing in lockstep with the expansion, is the cornerstone on which the whole edifice of structure formation rests. There is one great complication, and it leaves a fingerprint on the sky. The tidy proportional growth holds only after matter came to dominate the universe. Before that, in the radiation-dominated era that reigned until a redshift of about 3,400, dark matter fluctuations that had entered the horizon could barely grow at all. Overwhelmed by the smooth, fast-expanding sea of radiation, they stagnated, a stalling, known as the Meszaros effect. Only the larger fluctuations, which came inside the horizon after matter took over, escaped this suppression and grew freely. The result is that small-scale structure is suppressed relative to large-scale structure, and the divide falls at the scale of the horizon at the moment matter and radiation were equal. This is written into the shape of the matter-power spectrum, encoded in what cosmologists call the transfer function. The spectrum rises on large scales, bends over at a characteristic turnover set by that equality horizon, and falls away on small scales. The position of that turnover is a ruler, and measuring it weighs the matter content of the cosmos. A theory of statistics must meet a universe of observation, and the bridge is the galaxy redshift survey. Because the cosmos expands, a galaxy's light is stretched toward the red by an amount that, through the Hubble law, betrays its distance, so a spectrum yields not just a direction but a place in 3 dimensions. Stitch together enough such positions and the cosmic web springs into view. The first map to reveal its true character was the Center for Astrophysics survey, whose famous slice of the universe published in 1986 from a few thousand galaxies stunned astronomers. The galaxies lay not scattered at random, but arrayed along thin walls surrounding great dark voids, one sheet, the Great Wall, stretching more than 200 megaparsecs across the sky. Here, for the first time, was direct sight of the frothy, bubble-like architecture that theory had begun to predict. The universe was not a uniform dusting of galaxies but a web, and the race was on to map it. What began as a glimpse became, within 2 decades, a precise census of millions. The 2-degree field survey, working from Australia at the turn of the century, gathered reliable distances for more than 200,000 galaxies and measured the power spectrum well, enough to confirm the cold dark matter shape in detail. Then the Sloan Digital Sky Survey transformed the field entirely, imaging a third of the sky and taking spectra of millions of objects. Its baryon oscillation spectroscopic survey alone mapped someone and a 500,000 luminous red galaxies out to distances where the light set forth when the universe was half its present age. Today the dark energy spectroscopic instrument carries the work further still, its 5,000 robotic fibers drinking in thousands of spectra at once, mapping over 6 million galaxies and quasars, and through the absorption forests in distant quasar light, tracing the web back to when the cosmos was a small fraction of its age. The cosmic web has become a precision instrument. Woven into these maps is the most powerful geometric probe in all of cosmology, and it is a genuine fossil of the universe's first minutes. Before the cosmos cooled enough for atoms to form, ordinary matter and light were locked together in a single hot, glowing plasma. When a clump of dark matter tried to gather this plasma, the fierce pressure of the trapped radiation pushed back, and a spherical sound wave rang outward from every overdensity, traveling at more than half the speed of light while the dark matter stayed put at the center. These waves rolled outward for hundreds of thousands of years until, quite suddenly, the universe cooled, the electrons and protons combined into neutral atoms, the light broke free, and the pressure that drove the waves vanished. The expanding sound wave stalled where it stood, freezing into a spherical shell of slightly enhanced density surrounding each original seed. That frozen ripple is the baryon acoustic oscillation, and its radius is a length set by known physics in the newborn universe. That frozen radius, the distance the sound wave traveled before it stopped, is about 147 megaparsecs, and it is calibrated, almost from first principles, by the microwave background. Its consequence for the galaxy distribution is subtle but unmistakable. Across the whole universe, pairs of galaxies are very slightly more likely to be separated by that special distance than by any neighboring one. In the correlation function, it shows as a single broad bump at the sound horizon scale, in the power spectrum as a train of gentle wiggles. The landmark detection came in 2005, when Eisenstein and his colleagues sifted some 46,000 luminous red galaxies from the Sloan survey and found the acoustic peak sitting exactly where theory placed it. It was at once a stunning confirmation that structure had indeed grown by gravity from those primordial sound waves, and the delivery of a new and superbly precise cosmic ruler, one whose length the early universe had fixed for us. The value of a ruler of known length is that it measures distances, and the acoustic scale turns the whole cosmic web into a tool for charting the expansion of the universe. Observe the acoustic feature in a slice of galaxies at some redshift, and its apparent size on the sky reveals how far away that slice lies, while its extent along the line of sight reveals how fast the universe was expanding there. Measuring both the across the sky and the along the line of sight extent of the same physical ruler yields two quantities at once, the distance and the expansion rate at that epoch, and repeating the measurement at many redshifts reconstructs the entire history of cosmic expansion. It is this history that reveals the influence of dark energy. Because the acoustic feature is a fixed length imprinted before galaxies existed, it is beautifully clean. It rides through the messy, biased clustering of galaxies essentially untouched, a straight ruler laid against the growing web. Turning that ruler across cosmic time has become the central business of modern survey cosmology, and the dark energy spectroscopic instrument now performs it with unmatched precision. From acoustic measurements in galaxies, quasars and the intergalactic forests across a great span of redshift, its first-year results pin the matter density near 30% of the critical value and find the dark energy consistent on their own with a simple cosmological constant unchanging in time. But the headline is more provocative. When the acoustic data are combined with the microwave background and with distant supernova, they show a mild preference, somewhere between 2 and 4 standard deviations, depending on the supernova sample, for a dark energy that evolves rather than stays constant. It is a tantalizing hint, not a discovery, still short of the 5 sigma certainty cosmologists demand, and quite possibly a trick of subtle systematics. Whether dark energy is truly constant or slowly changing remains one of the great open questions, and the coming years of data are awaited to settle it. The same measurements feed 2 nagging tensions that may, or may not, be cracks in the standard model. The first concerns the present expansion rate of the universe. The value inferred from the early universe, from the microwave background and the acoustic scale together, comes out near 67 or 68, while the value measured directly in the nearby universe, from supernova, calibrated by variable stars, sits stubbornly higher near 73, the two disagreeing by 4 to 6 standard deviations. Because the early universe value leans on the calibrated length of the sound horizon, many proposed cures invoke new physics that would shrink that ruler, but none has yet convinced. The second tension concerns the clumpiness of the late universe. Some surveys of gravitational lensing and galaxy clustering find structure slightly smoother than the microwave background predicts, Both tensions are exactly the kind of unresolved debate that honest cosmology must flag rather than paper over. They may betray physics beyond the standard model, or they may dissolve into overlooked error. While the acoustic ruler measures the geometry of the expanding universe, a complementary probe measures its dynamics, how fast structure is actually growing, and comparing the two tests gravity itself. The tool is the peculiar velocity. A galaxy's measured redshift blends the smooth cosmic expansion with the extra motion its neighbor's gravity imparts, and that extra motion distorts the maps we build. On large scales, galaxies stream coherently toward overdensities, squashing structures along the line of sight in what is called the Kaiser effect. On small scales, their wild orbital motions within a cluster smear them into elongated spikes pointing at the observer, vividly named the fingers of God. The coherent large-scale squashing carries the signal, for its strength is set by the growth rate, the pace at which structure is assembling. That growth rate, read from these redshift space distortions across many epochs, is one of the most valuable numbers in cosmology. The growth rate matters so much because it is a direct test of Einstein's gravity on scales of tens of millions of light-years, scales unimaginably larger than the solar system where general relativity was first confirmed. The theory makes sharp prediction. The growth rate should track the matter density raised to a particular power, a growth index close to 0.55. That value is remarkably robust within general relativity, almost regardless of the details of dark energy. But rival theories of gravity, invoked to explain cosmic acceleration without dark energy, predict measurably different indices. One famous brainworld model, for instance, predicts closer to 0.69. To measure the growth index and find it sitting at 55 hundredths is therefore to put Einstein to the test across the whole visible universe, and to date the surveys broadly vindicate him, though a persistent hint of slightly slower growth, tied to that clumpiness tension, keeps the question honestly open. All of this rests on linear theory, which holds only while fluctuations remain small, and the most interesting structures form precisely when they grow large and the tidy proportional growth breaks down. The first insight into that nonlinear regime came from Zeldovich, who showed in 1970 that a collapsing cloud does not fall symmetrically to a point, but along its shortest axis first, flattening into a sheet or pancake, then along a second axis into a filament, and only last into a compact knot. This anisotropic sequence explains why the universe is webbed rather than a uniform scatter of blobs. Matter drains out of the voids into the walls, along the walls into the filaments, and along the filaments into the clusters that sit like spiders at the nodes where filaments cross. Small structures form first and merge into larger ones, the hallmark of the bottom-up assembly that cold dark matter dictates. The cosmic web is not a coincidence of arrangement, but the necessary signature of how gravity collapses a cold, clumpy universe. To count the structures gravity builds, cosmologists turn to an elegant model of collapse. Treat an overdense region as a tiny closed universe of its own. It expands with the cosmos, slows, halts and falls back, collapsing to form a bound halo. Linear theory, extrapolated to the moment of that collapse, gives a magic threshold. A fluctuation must reach a density contrast of about 1.686 to have collapsed by a given time. Press and Schechter, in 1974, married this threshold to the Gaussian statistics of the fluctuation field and derived the first prediction of how many halos of each mass should exist. Their formula captures the essence of a hierarchical universe. Small halos are abundant, while very massive ones are exponentially rare, since only the tallest peaks of the density field exceed the threshold. Modern refinements, calibrated against simulations and allowing for lopsided rather than perfectly spherical collapse, sharpen the count, but the physical picture Press and Schechter drew endures unchanged. It is worth pausing on the voids, for they are the dominant feature of the web by sheer volume, vast underdense bubbles, tens of megaparsecs across, that fill most of space while holding only a scattering of galaxies. They are not passive gaps but dynamic objects. Being underdense, a void gravitates less than the mean, so matter flows out of it toward its walls, and the void expands faster than the universe around it, growing ever emptier and rounder. Because their interiors are governed by the smooth dark energy background rather than by the messy astrophysics of galaxies, voids have become prized as clean cosmological probes in their own right, and threading through the whole picture is weak gravitational lensing, the faint, coherent bending of distant galaxies' shapes by the mass in front of them, which maps the total matter directly, dark and luminous alike, sidestepping the ambiguity of galaxy bias. Halos, filaments, walls, and voids together compose the vocabulary in which the nonlinear web is read. Where the pen of analytic theory falters, the computer takes over. Cosmological simulations follow the gravitational dance of billions or trillions of particles from a near-uniform early universe down to the present, computing the cosmic web directly. The challenge is that gravity is long-ranged, every particle pulls on every other, so the codes resort to ingenious hierarchies, solving the long-range pull on a grid and grouping distant matter into single tugs. The landmark was the Millennium simulation of 2005, which evolved some 10 billion particles in a great cube and reproduced the observed clustering of galaxies and the acoustic feature alike. But dark matter alone cannot make a visible galaxy. For that one must add the gas, the star formation, the black holes and their feedback, as suites like Illustris and its successors now do. Their remaining weakness is that the smallest processes must be approximated by tuned recipes, yet the agreement between a web seeded by inflation, grown through the standard model, and the one mapped by our great surveys is among the most quantitative triumphs in all of physical science.